Hi everyone, welcome to our introduction to chapter 3, acids and bases. As we dive into this chapter, let's just remember where we've been. We have had a home in Lewis structures. Hopefully we've had enough practice with Lewis structures that we're ready to cut the ties that bind us to that and move on to condensed and even skeletal structures. um, this idea of skeletal structures or bond line structures, Kukui structures, these guys right here are the epitome of organic chemistry. We are going to be using them thoroughly throughout chapter 3. So let's make sure at this point we've practiced enough, we feel relatively comfortable moving on. Again, if things are going too fast with drawing, take a step back and just practice your drawings and practice what information can be obtained from those. Because acids and bases are now moving into reactivity, right? We said this was going to be our very first time of seeing reactivity. Um, I chose all of these images because hopefully a lot of people have seen Breaking Bad. It was an awesome show. I used to watch it with my husband when we started dating. That's when it actually came out long time ago. And I just find this hilarious that yes, acids and bases are everywhere. It is probably not very common to find hydrofluoric acid in a high school chemistry lab. Funny story with hydrofluoric acid and Breaking Bad. I remember watching this show and specifically this episode with my brand new boyfriend, who, don't worry, he stuck around. We're married. And I sat there, they were trying to dissolve a body in the bathtub, and I smirked. And my boyfriend at the time looked over and said, "What's funny?" And I said, "That's not how you dissolve a body." And then I went on to proceed to tell him how to actually dissolve a body. Yes, he was quite freaked out, but again, romance, chemistry, it was there, so it's okay. Um, I think what's important to note is that when we see chemistry around us, whether it's on television, whether it's at the store, Home Depot, a craft store, there's all different types of acids and bases around us. And so as we're starting to dive into a couple of definitions of acids and bases, we'll try to bring up some real life examples in class when we discuss things so that we can see how important acids and bases are to our lives. Now, we're going to be using the Bronsted-Lowry acid-base definition. I know we've used the Arrhenius definition before in general chemistry. We're not doing a lot of equilibrium reactions here with water, and so the Arrhenius definition is not as appropriate for us. We're going to use the Bronsted-Lowry definition. Um, Bronsted-Lowry was another chemist who was brilliant, and he defined acids and bases as this. Acids donate a proton. Now, we've talked about this before. What does it mean to be a proton? Well, we know hydrogen has one electron in it, and what's in a hydrogen nucleus is one proton, and it has that one electron. This is the idea of hydrogen. Now, a hydrogen plus one cation has one proton and no electrons and no neutrons. So when we're looking at the definition of a proton, we are identifying a proton as this hydrogen plus one cation. That is what acids are defined as by Bronsted-Lowry. Bases, on the other hand, accept a proton. They will be going to pick up that hydrogen plus one cation. So it's this H plus one that will be transferring in from an acid to a base. Now, we recall this general chemistry example with HCl, hydrochloric acid, reacts with water. This was the acid. This was the base. Water was amphoteric. It could be an acid or a base. And in this case, it's a base because what we see is that base and acid exchange the proton. Specifically, the H, the highlighted red H there in HCl, goes to become H3O plus, which we are going to call the conjugate acid. And Cl minus, what's left over, is our conjugate base. Hopefully we remember this general idea from general chemistry of labeling acid-base, conjugate acid, and conjugate base. If you need a little definition of the conjugates, again, here they are. A conjugate acid is what results when the base pulls off the proton or accepts the proton. And a conjugate base results in when an acid gives up a proton, right? So looking at that link, the conjugate acid is linked to the base, and the conjugate base is linked to the original acid. So let's look at this example again. Let's just see what's happening. Slightly different molecules now. We still have water, but I wanted to throw in organic chemistry molecules now with it. And so when we look at this oxygen on the left-hand side with a -1 charge, what I want us to be able to see is, where is he in the product? Right there. And so what happened? Let's describe the journey that happened for that oxygen. Well, that oxygen must have gained a proton. He had a negative charge and no hydrogen, and now we see in the product that he accepted a proton. So oxygen minus on the reactant side is the base. What it becomes on the right-hand side, on the product side, is the conjugate acid. Water, on the other hand, had the hydrogen, and what we see is that that oxygen, let's just switch colors real quick, that oxygen now lost it in the products. And so we can see water, it must have been the acid. He donated that proton to the base, and what the leftovers become is the conjugate base. We'll start doing some curved arrows and see the actual transfer, but right now what I want us to be able to look at with this example is just the idea that we can verbally in English say what happened, locate and highlight some things. Protons are great to highlight. Those are typically highlighted in your textbook. I also like to highlight other things. I like to start to break down this reaction so that we can truly see what is happening. And kind of walk our way through it to start off with. Now, the making and breaking bonds involves electron movement. So when we use curved arrows, we are actually describing the flow of electrons, just like in resonance. Remember that we'll use the arrow that starts at the 2 electrons at the tail, and they point, the head points to where those electrons are going, right? And so when we're looking at these arrows, we're really just noting the flow. We use the same type of idea of curved arrows that we did with resonance structures, but here the big difference is now that we can actually describe the movement of electrons between different molecules, not just delocalizing electrons and only breaking pi bonds and lone pairs moving. Now we can see lone pairs moving, pi bonds breaking, sigma bonds breaking, atoms coming together, tearing apart. It's going to be fantastic. So let's go ahead and get some movement. We have a base and we have an acid. We're just going to use the generic B and HA right here. We have a conjugate acid. That's what results after the base picks up the proton. And we have the conjugate base, which is resulting after the acid lost the proton. Now, in terms of the curved arrow movements, the base has electrons, and I'm going to take that base's electrons starting at the tail of my arrow and point them, the head, towards the proton itself. When I do that, be very careful. This is not good. What's wrong with that? Negative formal charges do not tell me anything about electrons. The electrons have to move. What's wrong with this? It missed its mark. It's not even pointing at the hydrogen. Don't be lazy. Make sure you're direct with your arrows. The more direct you are with your arrows, think about these as your formation of sentences in organic chemistry. The more direct you are, the clearer you can visualize what's happening, and I can visualize what you know is happening, and you'll get full points. I'm very picky on my arrows only because they are truly telling the story of how the acid and base are reacting. Now, hydrogen here is making a bond with the base. Now, hydrogen cannot have two bonds. So as to not break our duet rule, the electrons held between H and A, that covalent bond must break and form a lone pair on A. Let's get some colors on here. These electrons from B minus have now become the covalent bond between B and H. The covalent bond between H and A is now the lone pair on A. So hopefully we can see that flow and see how the sigma bond is forming between the proton and the base, and see how the covalent bond between the H and the A is breaking. All right, let's do it again, just for practice. Now the base is truly attacking the acid. The base is going to pick up a proton. It's a base on a mission, and it wants that proton. So let's go ahead and give it to them. Any lone pair from the oxygen, but make sure you're originating at a lone pair, and make sure it's going to pick up the actual acid portion of the molecule, the proton. Protons can't have two bonds, so oxygen gains that lone pair. Let's just highlight some things again. Taking these lone pairs, it's now going to make one of the bonds between H and O in water. And this bond right here between H and O in the acid is now any old lone pair. It doesn't matter which one, you can just pick one. So that we can truly see that the acid cannot lose its proton without the base taking it. Those two arrows happen together. They happen all in one step. They're exchanging the proton, passing the baton, if you will. Now, the mechanism shows those two arrows that the two pairs of electrons from the base are going to make a new covalent bond, and the two electrons in the covalent bond of the acid are breaking to become a lone pair. Looking at this one, hopefully we can start to see that this is not just an acid-base reaction. This is a multi-step reaction that we will do later on in the semester in chapter 7. But what I really want to focus on real quick is looking at which one of these are called proton transfers, acid-base reactions. So take a minute and kind of just maybe pause the video and see which one actually looks like an acid-base reaction. A proton is transferring from one molecule to the other, from the acid to the base. Hopefully we can see it's this first one, not the second one, and this last one. These first and last steps are the proton transfers. They are both looking like an arrow pointing towards a proton, a hydrogen, and dumping some electrons on the leftovers. Before long, you'll be able to draw mechanisms all the way through, just like this one, not just the acid and base ones. Right now, don't worry about the rest of the curved arrows in the middle. We just want to make sure that we can truly understand a proton transfer. An acid-base reaction, by definition, is going to be the one that has a proton being attacked by a pair of electrons. And so that acid-base idea is going to hold true for all of our Bronsted-Lowry acids and bases. All right, let's get into quantifying acids. Quantifying meaning numbers will be able to be seen here. Now, how do we talk about quantifying acidity? What makes a good acid? Just a couple of things that I want to get out first. Using numerical data to compare how strong acids are. That term strong for an acid literally means that it is reactive. It's going to be good at donating a proton. So what does that actually mean at the grand scheme of things? It means that the bond between H and A, right? If we talked about this guy, this acid bond right here is actually reactive. It's going to be easy to break. The proton wants to leave, right? Those are all kind of different ways we can actually talk about the strong acid idea. Now, a strong base is going to be the same thing, reactive as a base, meaning that it is good at accepting a proton, right? Being able to donate that lone pair, we'll see that type of terminology used a little bit later. Being good at attacking an acid, ready to donate its electrons to make a new covalent bond between itself and the proton. All of those will encompass our idea of strong base. When we talk about weak things, they are the opposites, unreactive, bad at donating, bad at accepting. And so being able to say strong versus weak and really relating it to reactivity here is what we want to focus our attention on. Okay, so Kas, we've done Kas before. A Ka is the acid dissociation constant of the acid when it's dissolved specifically in water. It's a measurement of the acid strength with water as the base. Now, water is used just because it's a universal type solvent and it's everywhere, and we can easily look at the Ka, which was the products, A minus and H3O plus, over the reactant acid. Water in this equilibrium is such a high concentration that it doesn't change. It's also pure liquid, so it's not in the Ka. Now, a Ka is going to be the defining measurement of how strong an acid is. The acid was deemed strong if the Ka was greater than 1. That meant it was strong. If the Ka was less than 1, it's going to be a weak acid. Let's define that real quick. Strong what? A for acid, right? Versus weak acid. We did this a lot with doing ice tables. If you remember doing your ice tables and figuring out the initial, the change, and the equilibrium concentrations, guess what? We don't really do a lot of math in this class. So that's a good thing, I think. We're going to focus on what does it mean to be a strong acid, and how can we use that information to decide whether a reaction will happen or not. That's how we're going to quantify things. So here's the problem with Kas, and we said this a little bit in general chemistry, not too much, but Ka values range from 10 to the minus 50 to 10 to the 10. That is very difficult to work with. The reason behind the Ka being difficult to work with and why organic chemists don't usually use it is we like to do things without calculators. We don't really like to do a lot of math. And so this range is too big for us. That's really crazy to be able to try and handle when we don't even want to start doing long division or let alone pick up a calculator. So what we do instead is we actually take the negative log of the Ka and we get something called a pKa. Just like we took, let's just take a walk down memory lane. A pH is the negative log of the H plus concentration or the H3O plus concentration. That pH idea, P being the negative log function, is how we get this pKa. And this pKa is extremely helpful because what it does is it takes that log base 10 scale and it changes our 10 to the negative 50 to 10 to the 10 range, and it gives us a range of 50 to negative 10 now. So our pKa range has just gotten a little bit easier to handle. What was 10 to the negative 50 as a Ka is now positive 50. And what was 10 to the 10 for the Ka is now negative 10, right? The negative log. So we are checking those exponents, log base 10 scale, right? Taking the exponents, and we're going to negate them, change the sign. So big thing here, the lower the pKa equals, the stronger the acid. Why? It's because when we looked at that 10 to the 10, this is what we said favored products, right? And what I mean by favored products is we looked at that guy and we said 10 to the 10 meant that products over reactants for the Ka had 10 to the 10 more reactants than products. If we look at that number and how we adjust it with the negative log, that number, 10 to the 10, now becomes negative 10. And it still means the same thing. It favors products, right? So the lower the pKa, the stronger the acid. Just like if we remember, the larger the Ka, the stronger the acid. These two things go hand in hand. Just be very, very clear on which one are you talking about, the Ka or the pKa. We'll be dealing with pKas. So when we look at our pKa chart, this chart is the one in the textbook. You do have to know this chart. Why? I know it might seem silly. There's not too many on here. However, but what's really important, this is only a section of the chart that you need to know. I will have the full printout for you of the chart, but you can look at it in the textbook. What's really, really important with these numbers is the idea that you can get a baseline for reactivity. I'm not really in favor of memorizing for no good reason. However, when we start looking at these values in everyday reactions, not even acid-base reactions, when we start seeing these acids in a reaction, in a multi-step reaction even, we can start to justify how to draw our arrows, as long as we know the reactivity of the acid. Same thing for the base. The pKa tells us information about the acid, but it also tells us something about the conjugate base. And so looking at these, we can see H2SO4 is one of the strongest acids we have. pKa is -9, very, very reactive. And we can see here's the conjugate base. We have two little columns here of molecules. Acid is always tied to pKa, but conjugate base is important to note. A protonated ketone is around a -7, specifically for this one, -7.3. HCl is -7. H3O plus, -1.7 or -1.74, depending on how specific you want to get. Carboxylic acid functional group, we have acetic acid right there, which is household vinegar, has a pKa of 4.75. And the list goes on. But what we really want to be able to focus on here with these values is that this is how we actually quantify. This is how we can look at something and start to compare. So the first thing I want to compare is H2SO4 with a pKa of -9 and HCl on that chart with a pKa of -7. The change in pKa units here, just to compare, is 2. That does not mean that H2SO4 is 2 times as strong. Remember, this is a log base 10 scale. H2SO4 is 10 to the 2 times as strong, or 100 times. So H2SO4 will react 100 times more than HCl. That's how we're going to be able to work with these numbers. So remember where we get them. Yes, they're easier to handle because they're not exponents or times 10 to the blah, 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 blah. They're whole numbers, positives or negatives, but they're almost whole numbers. And we can start memorizing the whole numbers. You don't need to be exact on these measurements, or on these values, but I want you to know what they mean. It's a log base 10 scale, so any change in pKa is a log base 10 scale. 10 to the change is actually the difference in pKa units. So once we start reacting, why this is important is if you had H2SO4 and HCl together in a solution, you better be reacting that H2SO4. It's more reactive. It's a stronger acid. It's 100 times more reactive than HCl. HCl might be good for something later on, but it's not going to be the first thing to react. And that's how powerful these pKa units are for us. All right, using pKa's to be able to predict an equilibrium. Now, this is not looking at using a calculator. What we want to be able to do is utilize this idea. The higher the pKa, that means unreactive, weak acid. I also want to throw in the word here, stable. We like stable things, right? So the higher the pKa, it means the molecule doesn't want to react anymore. Think about where that molecule should be. It should be on the product side, right? We should see that the products are stable. The products are what we want to create, and we want them to stay. That's our desire in chemistry. So hopefully what we can start to see is that an acid and a conjugate acid are the two things that we can focus on with pKa's. pKa's only belong to acids, remember. So water has a pKa of 15.7. Tert-butanol, this one over here with the 4 carbons and the OH group, that has a pKa of 18 from our chart. What does that mean? 15.7 is lower than 18. So this reaction will go forward. What we notice here is that the equilibrium arrows favor the products. Products are favored because the conjugate acid is more stable than the acid. So there we go. Let me show you another one. Let's just hang off a hydrogen there. We'll leave a little empty box. We're going to decide, is this reaction going to go forward? Take a minute. Acid base, conjugate acid, conjugate base. Your main goal here is to make sure that you know which two molecules to compare and which two are going to have a pKa unit. Hopefully we got that. Acid is our carbon to hydrogen bond. The only reason why I hung off that hydrogen is so that we could see the curved arrows. Boop. Right, there we go. Hydroxide is the base. We have a carbon with a minus charge in the product and an H2O, water. Now, let's look at that acid. pKa for a hydrocarbon is 50. pKa for water, 15.7. Eek. Definitely not going to make a lot of products. We're going to favor the reactants because the reactants are so much more stable than the products. Higher the pKa. So in order to get a reaction to go, it should go from low pKa to high pKa, reactive to unreactive. If it does not, then the reaction is most likely not going to be a good one. Okay, sometimes we may not have pKa's. We may have forgotten them. We may just say, I don't need to memorize those. You're definitely not going to get full credit on the exam because there are going to be those questions. However, when we're looking at qualifying acids, we want to be able to determine a relative strength of two acids without knowing their pKa values. So we're going to compare their stabilities of the conjugate bases. The more effectively a conjugate base can stabilize its negative charge, whether that's a lone pair, usually, right? The stronger the acid. Let's repeat that. The stronger the acid, the more stable the conjugate base. Be very, very careful with this statement, conjugate base of the acid, right? So we're not looking at a specific reaction. We're just being able to look at an acid and say, is it reactive? Well, let's understand what it would become in an acid-base reaction. So when an acid loses that proton, it forms its conjugate base, and that has a lone pair of electrons that resulted when it lost the proton itself, and we need to determine the stability of that lone pair. Now, 4 different ways that we can look at that. The type of atom, the resonance, the induction, or the type of orbital that we have surrounding that conjugate base. We use the acronym ARIO. Now, when we use this, it usually works out probably 95% of the time. There are a couple of exceptions where ARIO doesn't always work out in this order, A-R-I-O. But A is the most important, then resonance, then induction, then orbital, right? So let's jump into A first. The type of atom carrying the charge. We'll just bring up this guy, butane, versus propanol. Relatively the same size. The only difference here is hydrogen attached to carbon and hydrogen attached to oxygen. So in order to compare ARIO with the A, in order to compare anything in this qualifying of acidity, we need to draw the conjugate bases. So draw the conjugate bases right here. Imagine if that proton was pulled off, the lone pair is put on to the atom carrying the proton in the acids. These are acids, these are conjugate bases. Now, we really want to be able to make sure that we are taking this step of drawing the conjugate bases and comparing these. This is now what we get to compare. Not the acids themselves. We compare the conjugate bases. All right. Here we can determine whether an oxygen or a carbon will be better to stabilize the negative charge. Well, there are 2 things that we need to be able to say. The more electronegative the atom, the more stable the negative charge. The other thing that we can look at, the larger the atom, the more stable the negative charge. These two concepts are important to be able to use together, right? But one thing I want us to remember, going across the periodic table from left to right, carbon, nitrogen, oxygen, fluorine, size changes a little, but electronegativity changes more. So across the periodic table of the elements, we would look at the electronegativity. The further we are to the right, the more electronegative, so therefore the more stable a conjugate base would be. But the larger the atom, when do we change size the most? Going down a group on the periodic table is when we actually increase the size. And the electronegativity changes a little bit, but not a whole heck of a lot. So when we go down a group, fluorine, chlorine, bromine, iodine is so huge. So when we think about the size factor, we go down a group. When we think about the electronegativity factor, we're going across a row. Here in this example, it's across a row. Carbon is further to the left. Oxygen is further to the right on the periodic table. More electronegative. So oxygen holds that negative charge better, more stable. It wanted that. So therefore, what we got to be able to think about is this conjugate base is more stable. The original acid, therefore, is a stronger acid. OH in propanol. Stronger acid because it yields the more stable conjugate base. Butane is what we would call the weaker acid. So which one should have the lower pKa? Stronger the acid, the lower pKa. Weaker acid, higher pKa. I'm trying to get all of the different types of things that we can talk about in comparing these two. Notice I didn't memorize any numbers. All I'm doing is looking at the trend, electronegativity or size. In this case, it's electronegativity, and then being able to talk a little bit about the acids based off of their conjugate bases, and that's stability. Excellent. Let's move on to resonance. Resonance, we know, is a stabilizing effect. It spreads out electron density across multiple atoms. It can spread out a negative charge. So, ethanol versus acetic acid. Biggest difference here is the idea that when we compare these two again, let's go ahead and draw their conjugate bases. Put in oxygen's lone pairs. See, I'm already getting lazy with those. Don't get lazy, Lauren. Okay. So what do we have here with these two conjugate bases that we can start to talk about with stability? Well, the conjugate base of ethanol has no resonance. There's nothing stabilizing that oxygen negative charge except for the atom. Well, if we look at the other conjugate base, the conjugate base of acetic acid, it also is an oxygen. So comparing apples and apples there. But what can this oxygen do on the right-hand side that the other oxygen couldn't? It was adjacent to a pi bond. So it can spread out its electron density in resonance. And when that happens, remember we have a resonance hybrid. And that means this is the more stable conjugate base. And this then is the stronger acid. Or lower pKa. Excellent. So resonance in the conjugate base is a stabilizing effect for that conjugate base. And therefore, if a conjugate base has resonance, its acid must be very, very strong, very reactive. All right. Induction, the I. Induction can also stabilize a formal negative charge by spreading it out, but induction is a little bit different than resonance. Resonance is an actual delocalization of an electron, right, around a molecule, multiple atoms. Now, electron withdrawing atoms or groups can inductively withdraw electron density from their surroundings and stabilize the negative charge. I like to think about this as aromatherapy. Now, if we were in a classroom together, I would always pull out a candle and just say, hey, here's a nice lavender scented candle. I'm going to light it and I'm going to spread out the scent of this candle to you, the rest of the atoms in the molecule of our classroom. Now, I'm not giving you my candle, but I'm spreading out some electron density towards you, and that is induction. If I were to hand you the candle, that's resonance. That's extremely powerful. That's, ooh, damn, you got my candle. But I'm not doing that in induction. I'm not actually moving any electrons. What I'm doing is just being able to spread out some electron density because I have electron withdrawing atoms. What are electron withdrawing atoms? Atoms that are electronegative. So something like this. Let's just take acetic acid again, and let's compare it to this version, where I put 3 chlorines. Trichloroacetic acid. What does trichloroacetic acid do when it's compared to plain old acetic acid? Well, these polar bonds, halogens are a great example here in induction. Oxygens, sometimes nitrogens, but halogens are awesome. They are pulling electron density away from that proton side, making the molecule polar. That doesn't happen with acetic acid. There's no induction or no extra induction right there. So nothing is helping make that hydrogen look more delta positive. Remember, we want it to react like a proton. We want it to be electron deficient. And so therefore, the chlorines here make that OH more reactive. They're not taking electrons in resonance. They are just giving a little tug of war on the polarity of the molecule. Now, why that happens is because the electron groups can actually pull the electron density away. So let's just kind of make this a little smaller. Those electron groups, if I were to react and draw the conjugate base, same induction is happening. Boop, 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 boop. All of these are trying to pull the electron density. Now look, opposites. We are trying to pull the electron density away from that negative charge, that formal charge of -1. That's helpful. It's not as helpful as resonance. That's why R comes before I in ARIO. but induction is still extremely helpful. Now we can look at pKa values just to be able to confirm that. There's acetic acid's pKa of 4.75. You put 1 chlorine on it, you drop it down to 2.87. That's almost a pKa change of 2. Again, about 100 times more reactive than that guy when comparing these two. Now let's drop it all the way down to trichloroacetic acid and look at that pKa of 0.7. About 10,000 times more reactive than the original. 10,000 times more reactive just because putting those chlorines on there. So very important induction. We see it usually with chlorines and fluorines. Again, the more electronegative you are, more induction, and that results in a lower pKa, right? The more chlorines or the more fluorines, that just how we see here, the more electronegative atoms result in a lower pKa because of more induction, more pull. Excellent. And also, just like this says, the closer the electron withdrawing group is, the more stable the conjugate base, the lower the pKa will be. Last one in qualifying acids, O for orbital. This one we're looking at the difference between sp3, sp2, and sp. Notice that the shorter the actual atomic orbital, it's holding those electrons closer to the nucleus. So when we look at sp, those electrons that would reside here in this orbital are actually closer in proximity to the nucleus versus electrons that would be here in the sp3. So looking at this one, we can consider the stability based off of proximity to the nucleus. Again, electrons attracting the protons, and so the closer you are to the nucleus, if you are electrons, the closer the electrons are to the nucleus, the more stable those electrons are. So let's just look at this kind of a thing. One big molecule here, but let's take each proton on its own and say, okay, I'm going to deprotonate over here on the sp2 guy and then redraw and compare it to the blue one over here. Be careful with that sp carbon in the blue. When the hydrogen gets pulled off, or the proton gets pulled off, the electrons go at that end where the carbon is right there. All right, so when we look at these two, what's important to note is to predict acidity, right? We still had to draw the conjugates. So now we can compare these two. This is an sp2 orbital holding a lone pair. And over on the right-hand side, we had the sp orbital holding the lone pair. Which one is holding the lone pair better? Well, if we look at the S character being the idea that there is lower energy, or it's closer to the nucleus, because remember S was smaller and lower in energy than a P, right? We still did have sub-level splitting. S's are lower in energy than P's. And so the lone pair in an sp orbital is closer to the nucleus. and therefore it's stable. What does that mean? That proton fix that double bond. That proton right there is going to be the lower pKa. It's the stronger acid. Because its lone pair that would result in the conjugate base is held in a more stable hybrid orbital. The sp is more stable to hold a lone pair than the sp2, and the sp2 is more stable to hold the lone pair than the sp3 because of S character, or what we call proximity to the nucleus. Excellent. And we can see that with just looking at the difference between sp3, sp2, and sp hydrogens. The sp3 carbon to hydrogen bond is extremely difficult to break. pKa of 50, it's the highest pKa that we have. Weakest acid, meaning that it doesn't want to be an acid. Ethylene with an sp2 carbon is a little bit better, 44, so a change in pKa units there of about 6. So, a million times better as an acid. And then we look at acetylene, the sp carbon, 25, pKa unit of 25. Think about the difference between these two polar opposites. Strongest acid in this group. There is a change of pKa of 25, which is 10 to the 25 times more reactive for acetylene than ethane. That's the magnitude that we're talking about when we want to think about acid strength. It's not that we're going to never react ethane. We can. It's just not as often. All right, so when assessing the acidity of protons, we are going to be using ARIO or pKa's. You will see both on your exam. There will be some times when we will ask you for the pKa and to determine whether a reaction will favor reactants or products in an equilibrium. Or we can also say, hey, here are some random ones. Pick the one that's going to be the best acid using qualifying techniques, ARIO, and maybe we'll ask you to explain why you choose what you choose. And so it's good to know both. So here's an example, ethanol versus propylene. Here is one where ARIO works out pretty well. Oxygen is more stable at holding a negative charge. So if these are the acids and these are the conjugate bases, it makes sense to say that oxygen holds that negative charge better. It's more stable than an sp3 carbon. And even though this sp3 carbon has resonance, in ARIO, A comes before R. So the atom is more important than resonance. And that works out great. Type of atom, oxygen versus carbon, is consistent. So even though propylene's conjugate base is resonance stabilized, A, right? The priority of ARIO, ARIO, is consistent. Here's one. In this example, we know that the equilibrium lies to the right because of the pKa values. But if we were to look at if we had to judge without those pKa values, let's pretend we covered them up, right? Or we forgot them. We could say, well, nitrogen minus versus carbon minus. Nitrogen holds a negative charge better. It's more stable. But in reality, ARIO doesn't always work out perfectly. Problem here is that even though nitrogen is better at holding a negative charge, even though nitrogen here would be considered maybe more stable at holding a negative charge. Remember, hybridization, that sp carbon on this one trumps over the electronegativity idea. So REO doesn't always work. For some acids, we simply just need to know the pKa values. There's exceptions to REO. Most of the time REO will work, but it maybe is 90%. I don't like A minuses, so get the A. All right. Now, with predicting equilibrium positions, any acid-base reaction, if we can think about those two different ways to predict the side that is favored. pKa values, you compare HA and HB, right? Acid and conjugate acid. The higher the pKa will be the favored side. Remember, higher pKa is the stable molecule. So that side is always favored. That's the side that the molecules are going to reside on most of the time. We can also use the relative stabilities of the bases, the base and its conjugate. That is REO. And again, the more stable the base, the side that is favored. We always favor stability, right? And so looking at predicting equilibrium, that's what we really want to hone in on. So let's just take this example. Let's draw one out. And I'll do the box again. And I'll let you look at it for a minute, maybe draw in some curved arrows, maybe label acid, base, conjugate acid, conjugate base, and then be able to judge how are you going to do this. Do you want to use REO? Do you want to use pKa's? And then pause the video, take a minute, and do that. Good luck. Now with this, we have acetylene or acetylide, the ion, 2 carbons triple bonded together. There is a hydrogen over here. You don't have to draw it, but there is one if you want to. That's okay. I'm going to leave it off so as not to muddle anything, but that is the base. And ethanol here is our acid. What happens in terms of curved arrows? Base always picks up the proton. The bond between the hydrogen and the rest of the acid is broken and placed as a lone pair on the conjugate. Here's the conjugate base and the conjugate acid. Couple different things. Now you can say for the conjugate bases, if we wanted to compare REO, we would predict that oxygen is more stable than carbon at holding a negative charge. So we would predict products. Great, awesome. If we wanted to use acid and conjugate acid, we could look at pKa's around 16 and around 25 for that sp3 or sp, carbon to hydrogen. Again, you don't have to draw in the H, but it's there if you want to. Low pKa to high pKa, product is higher, so therefore products are more stable. So products will be favored. In either case, using pKa's or using REO, this one works out. On an exam, we will hint towards which one we want you to use. If you understand the exceptions, and we'll go through quite a few of them in class, if you understand the exceptions to REO, you can work through that. But again, if we had asked you, hey, where's the pKa, and then predict, you'd have to be ready for being able to write out the pKa's as well. Okay, solvating effects. Now, because these are so similar, these two cannot be used with REO, tert-butanol and ethanol. They just can't. The pKa difference, tert-butanol is 100 times more stable than ethanol. Ethanol is 2 pKa units lower, so this is the stronger acid. Not by much, by 100, but not by anything that we would be able to judge with REO. So as with all acids, the difference in acidity is due to the relative difference or relative stability of their conjugate bases. And the ability of the solvent to stabilize those conjugate bases comes into play for this one. Namely, what we're looking at is the size of the conjugate bases. So when we think about ethoxide, or ethanol was the more reactive acid. So this one should be the more stable conjugate base. And what we can see is because there's less things around that oxygen, we have little things like hydrogens, that's fine. But over here we have 3 big CH3 groups. What I want us to start thinking about is this is what we call sterically hindered. There's a lot of things that could bump into other atoms on this molecule. And so that starts to bring in repulsions, right? And thinking about repulsions, we said that increases the energy, and that's not good. And so that's what's happening when we see some solvating effects. There might be some little changes in pKa's depending on what is around, not necessarily electronegativity or looking at induction, but just carbons and hydrogen groups. The more bulk you have around that negative charge in either conjugate base, you're starting to create steric hindrance. You're starting to create a blockage, like a brick wall, to stabilize that conjugate base. And so less stable, the more bulk you have. Nice. Okay, just to wrap up a couple more sections here, counter ions are usually known in general chemistry as spectator ions. They were things that we could eliminate in the net ionic reactions. When we did towards the end of the first semester of general chemistry, we tend to talk about ionic, molecular, and net ionic reactions. And anything that is a spectator, we always canceled out and said they don't change in the reaction. Typically, what we see as those spectator ions are cations from metals in this in organic chemistry. So they're always present. They are there. They need to balance out the charges of a solution, absolutely. But what we can start seeing is we don't often include them. So things like NaNH2, we actually split those up to Na plus 1 and NH2 minus 1. Let's put the formal charge on the atom that actually has it, which is the nitrogen. And same thing with sodium and hydroxide. We tend not to write sodium hydroxide. We tend to just write hydroxide now. Again, we'll put the negative charge on the actual atom, put the formal charge there, not the overall one. So looking at sodium, it is a spectator. It's sodium plus 1 on the reactants and sodium plus 1 on the products. So in reality, this reaction, as we would draw it maybe in organic chemistry, is with NH2 minus 1 reacts with H2O to form NH3 and OH minus 1. And so counter ions are important to be able to note. They are usually group 1 and 2 or 3 metals. So the plus 1s, the plus 2s, sometimes the plus 3 charges with aluminum. It doesn't mean that we can't write them. It means that they're there. They might need to be balanced, but we can also sometimes do what we do best with spectator ions and cancel them out. All right, one last definition of an acid base. Lewis, we know our American chemist, Lewis. He's an awesome guy, gave us the Lewis structure. And if you're pining for general chemistry at this point, because we've gone so far down the rabbit hole in chapter 3 that you want to start swimming back, this is where it gets fun. Stick around. Lewis was also an organic chemist. He started dealing with a new type of holistic definition of an acid and base, where he focused on what he loves to focus on, the electrons. And I find this definition really awesome because it actually is a good definition for any acid and base. We see an Arrhenius definition was when an acid or base reacts with water and it predicts products, H3O plus or hydroxide. The Bronsted-Lowry definition that we talked about earlier in this chapter deals with the proton transfer. But Lewis is really nice to focus on, because he says that an acid accepts a pair of electrons. And so when we think about that accepting of the electrons, that is true for organic chemistry when we draw out arrows. We're going to do that in just a second. A Lewis base donates the pair of electrons. And so let's look at this, this first one, right? We did this in general chemistry. We've done it in organic now. The base picks up the proton, kicks off the conjugate base, right? Cl minus. That oxygen accepted as a base. He accepted the proton from the acid, but also look what else he did. He donated a lone pair, right? Bases donate lone pairs. Acids accept pairs of electrons, right? So that idea of the flow of electrons is really beautifully seen in the Lewis acid and base definition. So let's look at the second one. This second one does not follow Bronsted-Lowry acid base. It doesn't even follow our Arrhenius definition. This is a weird one, but this is an acid-base reaction. It's a Lewis acid-base reaction. When we look, what happened is we made this new bond between oxygen and boron. Boron accepted the electrons. Oxygen donated some electrons. Oxygen donates electrons and boron accepts them. Big difference. It's not a proton transfer anymore. This type of acid-base reaction for Lewis acid-base reactions is looking at just the flow of electrons. So here we have a Lewis base and a Lewis acid. Most often what we see for just pure Lewis acid-base reactions, we could see one arrow. That's very typical. And we also could see a joining of two molecules with formal charges as the products. And so let's just do one more for fun. A good indication that it could be Lewis also is when you see that Lewis acid is a group 13 or 3A metal, or boron, which is a semimetal or a metalloid. Now, for this reaction, or these types of reactions, what I want us to be able to focus on is seeing the holistic picture. Oh, I won't make it too long. Of reactants and products and being able to label. There's no qualifying or quantifying these types of acids. It's only going to be labeling acid, base, conjugate acid, conjugate base. Or I'm sorry, not even conjugates, just Lewis acid and Lewis base here. And maybe some curved arrows. So what we see again is a new bond between the nitrogen and the aluminum. Nitrogen must have donated its lone pair. That is what we call the Lewis base. Aluminum accepted that lone pair to make the bond, so therefore it's the Lewis acid. You would not define anything here over in the product side, just Lewis acid and Lewis base.